The human eye is an amazing mechanism, able to detect anywhere from a few photons to direct sunlight, or switch focus from the screen in front of you to the distant horizon in a third of a second. In fact, the structures required for such incredible flexibility were once considered so complex that Charles Darwin himself acknowledged that the idea of their having evolved seemed absurd in the highest possible degree. And yet, that is exactly what happened, starting more than 500 million years ago. The story of the human eye begins with a simple light spot, such as the one found in single-celled organisms, like euglena. This is a cluster of light-sensitive proteins linked to the organism's flagellum, activating when it finds light, and therefore, food. A more complex version of this light spot can be found in the flatworm planaria. Being cupped rather than flat enables it to better sense the direction of incoming light. Among its other uses, this ability allows an organism to seek out shade and hide from predators. Over the millennia, as such light cups grew deeper in some organisms, the opening at the front grew smaller. The result was a pinhole effect, which increased resolution dramatically, reducing distortion by only allowing a thin beam of light into the eye. The nautilus, an ancestor of the octopus, uses this pinhole eye for improved resolution and directional sensing. Although the pinhole eye allows for simple images, the key step towards the eye as we know it is a lens. This is thought to have evolved through transparent cells covering the opening to prevent infection, allowing the inside of the eye to fill with fluid that optimizes light sensitivity and processing. Crystalline proteins forming at the surface created a structure that proved useful in focusing light at a single point on the retina. It is this lens that is the key to the eye's adaptability, changing its curvature to adapt to near and far vision. This structure of the pinhole camera with a lens served as the basis for what would eventually evolve into the human eye. Further refinements would include a colored ring called the iris that controls the amount of light entering the eye, a tough white outer layer known as the sclera to maintain its structure, and tear glands that secrete a protective film. But equally important was the accompanying evolution of the brain, with its expansion of the visual cortex to process the sharper and more colorful images it was receiving. We now know that far from being an ideal masterpiece of design, our eye bears traces of its step-by-step evolution. For example, the human retina is inverted, with light-detecting cells facing away from the eye opening. This results in a blind spot, where the optic nerve must pierce the retina to reach the photosensitive layer in the back. The similar-looking eyes of cephalopods, which evolved independently, have a front-facing retina, allowing them to see without a blind spot. Other creatures' eyes display different adaptations. Anableps, the so-called four-eyed fish, have eyes divided in two sections for looking above and underwater, perfect for spotting both predators and prey. Cats, classically nighttime hunters, have evolved with a reflective layer maximizing the amount of light the eye can detect, granting them excellent night vision, as well as their signature glow. These are just a few examples of the huge diversity of eyes in the animal kingdom. So if you could design an eye, would you do it any differently? This question isn't as strange as it might sound. Today, doctors and scientists are looking at different eye structures to help design biomechanical implants for the vision impaired. And in the not-so-distant future, the machines built with the precision and flexibility of the human eye may even enable it to surpass its own evolution.